So let's have another look at finding area between curves. All right, now let's have a look. We've got two curves and we're interested in the region they cover when they intersect between them above the x-axis. So in this particular case here, we have f of x on top and we have g of x underneath there. And we're interested in this region between a and b. That's that bit in there. Now the integral, that area there, will just be the integral from a to b, f of x minus g of x. Now what f of x will do will give us, integrating between a and b, will give us everything under f of x right down to the axis here. Okay, it'll give us all of that. All right, so including that bit will give us all of that. But then what happens is when we integrate g of x, the straight line there, then the integral between a and b for that will give us all the area under the line and between the horizontal axis. It'll give us all of that. So what happens is that area is counted twice, first by the integral from f of x between a and b, and then g of x between a and b. And so when we subtract it, we will cancel out. So this bit that's shaded in red will just be cancelled out. We'll be left with the area under f of x between a and b, subtracting from that the area under g of x from a to b, and that just leaves over the black shaded region there. Okay, that's above the axis. If we have the same situation reflected about the horizontal axis, and we now have some curve there, p of x, okay, is underneath k of x, okay, then we can do the same thing. We just take the absolute value of it, okay. The area under between p of x and the horizontal axis between a and b will be all of this. That's everything, including the black shaded bit. So it's everything between p of x and the horizontal axis. It's below the axis, so it'll be a negative result. If we now subtract from that the area under k of x between a and b, okay, we'll be left with this black shaded region again. And we take the absolute value because so that we get a positive result. Okay, remember the integral gives the value, the signed value of the area between the curve and the horizontal axis. If it is below the horizontal axis, it's going to give you a negative result. You must use the absolute value. Okay, now let's look at an example here. Let's take this. Find the area enclosed by f of x is x plus 1, a straight line there. Okay, and the area enclosed between f of x is x plus 1 and g of x is x squared minus x minus 2. So the area between the straight line and the quadratic, the parabola here. Now we can split that down into, if you like, we can calculate it as being 3 areas. You don't actually need to do that. I will show you a simpler one shortly, but let's just have a look anyway. Let's split it down to the triangle here, A1, okay, between minus 1 and 2, and up here to y equals plus should be plus 3. Okay, then A2 from x equals 2 to x equals 3, that's where they intersect to give us A2, and then we can do the bit underneath the curve here where we will need the absolute value sign. So underneath the horizontal axis where we will need the absolute value sign for A3. First, let's find the intersection points. So they intersect at x squared minus x minus 2 is equal to x plus 1. Okay, so subtract x from the right, subtract 1 from the right, we're left with x squared minus 2x minus 3 equals 0. You can factor this, factors of 3 are a negative 3, and 1. Factors of x squared are x, and x minus 3 times x plus 1 expanded out will give us our original x squared minus 2x minus 3. Set to 0. Null factor law gives us x equals plus 3, x equals minus 1. So we have an intercept at x equals minus 1. Substituting x equals minus 1 into f of x will tell you that it occurs at f of x equals 0. Okay, right there. And at x equals plus 3, we substitute 3 in there, we'll get y equals 4, f of x equals 4. All right, so there we are. Okay, we can split the area down into, we'll split the area down into A1, A2, A3. So for area 1, we have the integral minus 1 to 2, of the area under x plus 1, the straight line integrated with respect to x. For area 2, we're going to have the integral of x plus 1, the straight line, minus the curve underneath, which is x squared minus x minus 2, All right, so what will happen there is you get the area under x plus 1. Okay, so it's all that up to 3. But you then subtract from that the area under the curve. So that gets taken out again, and we're left with the difference, which is all that bit in there, A2. Okay, now for the A3 here, that's the curve which goes below the horizontal axis. We just want the area in that covered by that region from x equals -1 to x equals +2. But we're going to have to take the absolute value because the result will be a negative answer, and we don't want negative. You can't have negative for area, just like you can't have negative value for length. So what we have now is plus the absolute value of the integral -1 to 2 of the curve x squared minus x minus 2. Okay, so evaluating these, x plus 1 gives you x squared on 2 plus x when anti-differentiated. There's the terminals. Same thing here, subtracting all this and evaluating it, we will have, well, you could have minus x squared here, becomes minus x cubed on 3. X plus x is 2x. Okay, that becomes x squared on 2. The 2's cancelled, so we're left with just x squared. Plus 1 plus 2 is plus 3. Anti-differentiating that, we get 3x. Terminals are 2 to 3. Okay, and then finally we have the absolute value of x cubed on 3 minus x squared on 2 minus 2x, and we're evaluating between 2 and -1. Okay, so let's do that. Next line down, evaluating the first result between -1 and 2 gives you this. The next bit, evaluating it A2, the second integral between 2 and 3 gives you this. And finally, the third one here, evaluating between -1 and 2 with the absolute value signs outside. Altogether, when we add this, we'll get 32 on 3, or 10 2/3 units squared. Okay, so I made a big point of doing all that. In reality, though, you only need to do the integral of the top curve minus the bottom curve, and that will take away all the negatives, and you'll get the exact same result. The integral x plus 1 minus x squared minus x minus 2, okay, integrated between -1 and 3, okay, evaluating that, minus x cubed on 3 plus x squared plus 3x, evaluated between the terminals, gives you the same results, okay, 10 2/3 units. And the reason for that is, again, much simpler to do, just the top curve minus the bottom curve, okay, so what you're getting is the area under here and the horizontal axis. So you get that triangle there, and then you subtract from that, okay, the area under here, which is positive because you don't want to include that, so that gets subtracted. Because remember, the integral for the quadratic part, x squared minus x minus 2, that'll give you a positive result there, but you're going to subtract that away from here because it's already been counted twice when you integrate it under x plus 1. Okay, the area under the curve, the straight line x plus 1. Now here, you're subtracting the integral for this region here, okay, all right, and what that's doing when you take, by subtracting, you're taking the negative of what is a negative result, and so it gives you a positive. All right, so in this case you didn't need to split it into 3 regions. You can simply do the top curve minus the bottom curve between the terminals.